Hey kiddos, here's the review for Spiral 12. Starting off, we've got some kind of a thing that we can barely read. So I'm going to rewrite this integral part just so we can understand what's going on here. So that tells us that f of x is equal to the integral from a to x of h of t dt, and we have the graph of h up above. What this is basically saying is that if I were to take the derivative of this, we'd have h of x, and that's going to be equal to f prime of x. What that's getting at is that one of these pictures is going to have this as its derivative. So this is weird because it's kind of going way back to derivative stuff, but at the same time, it's kind of looking at notation from our current FTC stuff. I highlighted the 0 point there because before this we've got a positive derivative, which means we're looking for a graph that up until this point has a positive slope. In other words, is increasing up until the point B. Alright, so let's just kind of go through these things. Up until B, A is increasing. Up until B, B is not increasing, goes up and then down. Up until B, C is not increasing, goes down and then up. And for D, well, this is getting easier than it looks. No, because that's decreasing. And then for E, well, that's increasing up until B, so we're good. Okay. The next part is that our graph is negative here, and that means that we're going to have a negative slope at this point, and both A and E, which are the only ones have left, have negative slopes, so both of those are okay for that. The next thing we might look at, I'm going to erase my little tick mark here, is that this is a really nice smooth curve. We're going from positive to 0 to negative in a really nice orderly fashion, which means that our graph is going to behave pretty well. And comparatively, this has what some teachers call a doink point. It's going one way, then doink, it goes another. Do not write that on any test. You will not receive credit. But this is a place that is pointy. And here the derivative would not exist because of that. The derivative pretty clearly exists and is 0 at B. So we're left with this one, which has a maximum at B and therefore works the way we want it to. For number 20, we've got, I don't even know why these are numbered. These numbers don't connect to anything. I think they're just taken from whatever assignment we grabbed these from long ago for the reviews, but that's okay. So we've got g of x, and we've got f of x is equal to g prime of x, okay. And then we've got the antiderivative of f of x. Okay, so I'm going to replace that with g prime of x and talk about this as the integral from 1 to 3 of g prime of x dx. And this is understanding that derivatives and antiderivatives are opposites. Derivatives and integrals are opposites. So we're looking at g of 3 minus g of 1. We're given g, so we can just plug 3 in, plug 1 in, and we're done. G of 3 is going to be 9 minus 9 is 0 plus 4. And then g of 1 is going to be 1 minus 3 is negative 2 plus 4 is 2. 4 minus 2 is going to be 2. For number 12, because 20 and then 12 makes sense, we've got f prime of x equals 2 over x, and f of the square root of e equals 5. Okay, going from f prime to f means we're doing an antiderivative, and we're going from 2 over x, which I'm going to rewrite as something else. I'm going to write that as 2 times 1 over x. And we know that when we're doing something like the antiderivative of f prime of x, from A to B, that's equal to f of B minus f of A. So one of the things that we can do here is kind of create some kind of a starting point. And I could either treat this as some kind of almost a differential equation, where when I take the antiderivative of this, which by the way is going to be 2 times the natural log of the absolute value of x. We're probably not going to need that absolute value, but I'm going to keep that in here anyway. Then we got, I don't know why I did plus 5. Actually, I do, because I can see a 5 here, and it makes me want to do that. So we got plus c. And then if I plug in this stuff, so 2 times the natural log, I'm going to write this as e to the 1/2, and then plus c is equal to 5. The natural log of e to the 1/2 would be a half, times 2 is 1. And if plus c is equal to 5, that means that c has to be 4. And that gives us something to work with. So we've got 2 ln of the absolute value of x, and then plus 4. So if we're trying to find f of e, this is f of x. Ooh, I changed colors accidentally. When I plug e in, we get 2 times the natural log of e plus 4. Natural log of e is 1. 2 plus 4 is 6. Next up, we've got substitution and differential equations. All right, here we've got, that looks like a big F prime. We've got a function being defined. Ooh, this is like a theoretical function thing going on here. The big thing I'd like you to notice is that we have a function inside a function. Therefore, we can set u equal to 2x. That means du dx is going to be 2. And dx is equal to du over 2. So when I plug this in, and we're going to get some fun calculus only would this ever happen things going on here, we get f of u, and then we've got du over 2. The other piece that we can change here is that this is going to be 3 is equal to x. If I convert that to u, we said that u is equal to 2x, so u would be 6. And for the bottom, if that's equal to x, that means that u would be 2. So I'm going to rewrite this as the integral from 2 to 6. And I'm going to take that 2 under the du, put it out front as a half. Then we've got f of u du. Okay. That's going to be a half big F of u evaluated at 6 and 2, which is going to be a half f of 6 minus a half big F of 2. And that happens to be E. All right, number 18, which there's barely any room for. I'm going to try to do this off to the right. We've got e to the tan x over cosine squared x dx. And when we do this, one of the comments that I've made is that anytime you have something inside of an exponent, that's going to be your u. So u is going to be tangent of x. Du dx is going to be secant squared of x. And that tells us that dx is going to be du over secant squared of x. Okay. I'm also going to plug some stuff in for these guys. So we've got the antiderivative. Tangent of pi over 4 is 1. Tangent of 0 is 0. And then we've got e to the u over cosine squared of x times du over secant squared of x. And you might recognize that cosine squared and secant squared are reciprocals. Therefore, when you multiply them, they turn into 1. And then we finally have something we can integrate. So that's going to be antiderivative of e to the u is e to the u. Plugging 1 and 0 in, that's going to be e minus 1. Which is, ooh, that's interesting. You've got an, oh, okay, I didn't see that middle one. I thought we were going to have an e plus 1, and I had lost a negative somewhere, but I didn't see that e minus 1. For the problem appropriately labeled 84, no apparent reason again, we're looking at a differential equation, dy dt is equal to ky, where k is a constant, and we've got to do some kind of a separable thing. So let's take a look at this. I'm going to do this as dy is 1 over y, and then on the other side we're going to have k dt. When I integrate both sides, we get the natural log of the absolute value of y. This is a population, everything's going to be positive, so I'm not going to need that. And then we've got kt. That's going to give me e to the kt is equal to y. So the big piece here is that if we have some kind of a population that's doubling, so we've got some kind of population at year 1, which we'll call y1, or just y, and that's equal to e to the kt. And of course, oh man, I'm being terrible. I forgot my plus c. Oof. I would be so mad at myself if I were grading myself here. And the way we're going to deal with this is that if we have a population of 2y, that would be at e to the 10k, I put in 10 for t, plus c. When we're looking at this, what I might suggest is taking these constants, moving them down front. So we get, for the top equation, y is equal to ce to the kt. And if we're talking about this in year 0, we'd be talking about a value of c. And this would be 2 times that y initial value, ce to the 10t. So here's the thing, we're kind of stuck until we figure out what we want the population to be, or if we do some more intense algebra stuff. Since we don't know what the starting population is there any reason that we can't just say this is something like 1 is equal to ce to the k times 0, since that's our starting thing. And that would let us set c is equal to 1. I like how I wrote c is equal to c there. And that would mean that 2, that doubled population, is equal to 1 e to the 10t. And if we want to get that out of that exponent, we've got to take the natural log of both sides. And we get the ln of 2 is equal to 10t. So ln of 2 divided by 10 should be our k value. So one of these values is going to be ln of 2 over 10, and that's going to be a. And then finally we've got area and volume. The big idea here is that you're going to have to at least show the setup for these You probably don't have to do the integration for many of these, but you do need to show the setup in order to get credit for getting the right answer for these. While I'm explaining this, I'm just getting some Desmos stuff open so I can get the decimals for these as we go. Okay. For 92, we're talking about the area under the curve for cosine of x from x equals k to x equals pi over 2. So we're talking about from k to pi over 2, area under cosine of x dx, and that's going to be equal to 0.1. Okay, antiderivative of sine is cosine, derivative of cosine is sine, so that's going to be sine of pi over 2 minus sine of k is equal to 0.1. Sine of pi over 2 is 1. 0.1 minus 1 would be negative 0.9, which means that sine of k is equal to 0.9. Sine inverse of 0.9 is going to be equal to k. And when we do that, we get 1.119, which is 1.120. For 25, we're looking at the area between two curves from 0 to 2. So the first thing that I want to do is just kind of sketch a graph of this. Just so I know what this thing looks like. We've got y equals x squared and y equals negative x. So it's something like this, since we're talking from 0 to 2. We don't have to worry about where those things intersect as much because it tells us what we're looking at. But we do know the parabola is going to be on top. So we're integrating from 0 to 2. X squared minus negative x. That's going to be x cubed over 3 plus x squared over 2, going from 2 to 0. So that would be 8 over 3 plus 4 over 2, and then to minus 0. 8 over 3 is going to be 16 over 6. 16 over 6 plus 12 over 6 is 28 over 6, which is 14 over 3. All right, 92. We're looking at a region bounded in the first quadrant below x squared. Hey, we just did that. Or we just talked about that. And above by the way, that's the worst parabola I've ever seen. I'm going to erase that because it's embarrassing. It's bounded below by x squared, so I'm going to actually try to draw this somewhat appropriately. And above by the square root of x. The only thing we really need here is that point of intersection, which is going to be 1, 1. So really, if I zoom in, we're looking at a section of the graph that looks like this, going from 0 to 1. All right, it says that cross-sections perpendicular to the x-axis are squares. We got squares coming out of our screen at us. And that's going to be an area formula of a of x is equal to side squared. Okay. We also know that the side is going to be the top minus the bottom. So in this case, that's the square root of x minus x squared. And that tells us that our integration is going to be the integral from 0 to 1 of the square root of x minus x squared, all squared, dx. And again, this is a calculator active problem. So when I go from 0 to 1 and I set this up, I'm just typing this into Desmos as we speak. So we got the square root of x minus x squared squared dx, and I get 0.128. and that's going to be our first value, 0.129. You got to show the setup, and then you can use fnint to evaluate that. Number 23, we've got a region enclosed by the x-axis, the line, sorry, I just read that as the x-axis, it definitely says the y-axis. The line y equals 2, and the curve y equals x. Sorry, y equals the square root of x. So that's looking at this. And we're revolving this around the y-axis. Oh, I like how I did x equals 2 instead of y equals 2. That's why we're having some issues. And I'm going to erase that lovely red stuff, and now we're good. So we're talking about this area in here, and we're spinning it around the y-axis. The first thing we need to know is that we're integrating from 0 to 2, but in the y direction. So I'm going to write y equals 0 and y equals 2. That's going to mean that we need some kind of a dy, which means our equation has to be in terms of y. So if we've got y equals the square root of x, and we wanted this in terms of y, we could write this as y squared is equal to x. And because we're going horizontally instead of vertically, that's what we're going to integrate with. Okay, this is going to be pi r squared, and the radius is going to be this curve minus the axis. So that's going to be y squared squared. All right, I'm going to integrate this. So that's y to the 4th, which means that we're looking at y to the 5th over 5. You can keep that pi there. Plug in 2, plug in 0. 2 to the 5th is going to be 32. And I'm going to put my pi after it over 5. And minus 0 means it doesn't matter. We end up getting just 32 pi over 5 as our answer.